Good afternoon, everyone. Welcome to EVA and Division for Chemical Engineering. My name is Martin Malmström. I'm the chairman of the division. And today we'll have a seminar on machine learning, the chemical industry in the starting blocks. I think being more on the pharmaceutical biomedical side of things, I'm sort of constantly marveling at this and being both inspired and a little bit scared of the rapid developments that are currently going on in the broader area of artificial intelligence. Of course, we see these huge opportunities in the way that products are being developed, produced, marketed, increasingly also regulated in some areas, as well as, of course, the more as private persons, the developments that we see going on in countries like China, for instance, and also the corporate ownership of personal data as a commodity almost. Now, this is a very broad question, and the Academy is working with quite a few facets of that. Today, we're being much more concrete. It's about machine learning in the chemical industry setting. The initiator to this seminar and the mastermind is Magnus Nydén. And before I leave, he's a member of the division, and in his everyday work, he works at a company called Liquid Wind, where he's CTO. Before I leave the word to Magnus, I just want to thank you for taking the time to organize this thing, and of course to all of you to come here. So I hope you will have a interesting workshop, and of course that you will participate in good discussions afterwards. So welcome, and looking forward to the seminar. Thank you.
Thank you, Martin. Can you hear me all right, everyone? Good. So, let's see. Jan, how do I... Where is Jan? I can't see him. I guess my presentation is here somewhere. I actually need Jan's help. Is he here somewhere? Okay. Okay. Let me then initiate before that. So I'm a trained chemist. Did my PhD in Lund University in physical chemistry. And can you help me just to start the presentation? I don't know where it is really. And I tried desperately to get my now 21-year-old daughter to study chemistry, and I failed miserably. Turns out that she's going down the route of studying finance and economics instead. What a failure. And then I start to read about economics. The very basics of economics was my former colleague at UCL who taught me. Anyone know the fundamental, at least one of the, I guess, fundamental definitions of economics? Anyone know? Dare to take a chance? The study of choice. That's what it is. This is really interesting, isn't it? Because it depends on everything that goes around you, your external influences, what happens inside you, the biology, the chemistry inside you, and at that interface, you make decisions. You buy a new car, or you buy a green fuel to your car, or you don't. All choices made. So all of a sudden, economics to me became extremely interesting because it's such a complex thing. It's not about numbers. It's about behaviors. So I started to listen a lot to the big people out there. Who are the best economics lecturers? Who's the best in the world? And I particularly fell for one person who is... He's a senior professor at the Wharton Business School. Teaches a lot of the Fortune 500 companies, CEOs, for instance, in sustainability in economics, among other things. Some of the things that I will mention here today actually comes from him. And I would urge you to look into the talk, and you will see the reference to him later. His name is Jeremy Rifkin. But before that, I'm going to talk just a few words about this little company. But before that, point to the fact that this is about the digital transformation. And the chemical industry needs to probably get out of the starting blocks soon, I feel. So this is my name, Magnus Nyrén. I'm the CTO and Public Policy Director of Liquid Wind. I should also mention Thomas Andersson, because he has helped me with some of the slides and the thinking behind this presentation at Siemens. And I think there are some people from Siemens here, if I understand correctly, too. Okay, good. Oh, I made the reference, so please tell Thomas. So very briefly, although some people may not like it, but the business around carbon dioxide is changing. And soon it's, and perhaps even now already, it's now becoming viable to, in some niche markets, to work with CO2 as a basic starting material, especially if the CO2 comes from biogenic sources. Because some of the end users of materials or fuels are saying we are interested in a new fuel or a new material, should it come from biogenic sources, not from fossil sources. Interesting, because the climate actually doesn't care, but that is what we are hearing, and they're willing to pay a significant premium for that. So what we are going to do in the company is to take renewable electricity. We're going to work at 50 megawatt power, use that much electricity per year into an electrolyzer where it uses water to make hydrogen and oxygen. Combine that with a carbon capture unit, for instance, on a pulp and paper mill, captures 70,000 tons of CO2 per annum. Combine that together with hydrogen in a methanol reactor by Haldor Topsoe, Danish company, and then make electrofuel in the form of e-methanol. And then our main focus is actually the cruise line industry, where there is an appetite for greenifying, if you like, for obvious reasons. Because if you think about it, it's not really a industry that is that sustainable, and they're struggling with their business case at the moment. So this is the size of the plant that we're anticipating. And then, of course, we go to the bank and we look for money for funding of this. It's about 1 billion Swedish kronor, 100 and odd something million euros. And then they say, okay, you're working with the biggest company in the world in this, it's Siemens, which is great. You're working with Haldor Topsoe, which is great, that adds a lot to the bankability. You're working with a small company for the carbon capture unit. That's okay, they have strong patent situation. But overall, we're lacking some details on the bankability of this project. We're not really considering you're bankable yet. So what can you give us in terms of bankability? And then we say, well, what about this? And then they love that because it's a buzzword at the moment, but no one really knows what it means, perhaps at this point in time, because it is a very broad beast. And Kostas will be the first one to tell me, yeah, but what problem are you going to solve? And we will hear more about that later on. So there are many definitions. This is something I stole from this is the wrong reference. I can come back to that later. A digital twin, and the general idea with it, on using data as a twin to a real plant, if you like, is to generate knowledge from that data in order to transform the company into a learning, agile organization and enable rapid decision-making and adaptation processes throughout every part of the business and across all business process areas. The acquisition of this agility provides companies with a significant competitive advantage in a disruptive environment. Okay, that sounds good. Then the financiers see this and they say, okay, if you can achieve this, that adds to the bankability. Therefore, the digital twin is important for a small company such as ours. So today, I will give you my view on the global drivers for development of a digital twin. After me, Kostas, you will introduce yourself, Kostas, is from London, whom I've gotten to know over the last 5 years as, I would say, the leading expert in the world on process science-related digital twins. I think you call it a process twin, if I understand things correctly. Go into a broad view on what a process science twin perhaps is, and some of the technologies behind it, where machine learning is one. And then, Staffan, you will introduce yourself as well. We'll go into maybe a little bit more narrow to the pharmaceutical industry and applications within the pharmaceutical industry, where machine learning is a key method of choice. But I'll leave it to the two of you to make a much more fair introduction of yourselves and what you're going to talk about in detail. So let me then continue on this one here, the disruptive environment, because I think that is the key thing here. So when you go into YouTube and listen to Jeremy Rifkin, the senior professor at the Wharton Business School, you will hear him saying these things over the course of 55 minutes, largely. I've just extracted bits and pieces of it. The disruptive environment is an environment that is coming now, probably because of serendipity. But what characterizes the environment at the moment is a low GDP over the last 20 years, which he argues comes from the fact that we've had many years of low productivity. But the question is why? Well, the theory at least is that we are stuck in the second industrial revolution, which utilizes fossil fuels as the raw material. And if you think about it, the whole economy today is based on fossil fuels. And if you remember in 2008, when the Brent crude oil, I think, hit 147, the whole economy shut down. And then you remember a few months later, the subprimes in the United States crashed. The argument is that that was just the aftershock. The real earthquake was when the crude oil hit 147, because all investment stops, all, because it is based on fossil fuels. The whole economy is based on fossil fuels. And the fact that, according to the economics, Germany hit maximum productivity in the fossil fuel area, I believe, 10 years ago, 18%. Japan hit 20% as the maximum, and United States, I think in 2006, if I remember correctly, came up to 16% productivity, which is not very impressive. But that is, of course, because of all the losses you have in the vertical integration along the fossil fuel-based economy. So, first and second industrial revolutions, let's go back to that, because you probably know this, but the definitions, at least, that most seem to be agreeing on is the fact that the first industrial revolution occurred sometime between 1760 and 1840, or continuously, I should say, where the German print press went from being manual to machine-driven, steam, from coal power, so much faster. So books, we printed books. That's why the whole university system could really explode, because we could produce books much faster. Also, the British laid out the telegraph system across the aisles. So 2 new modes of communication happened like that. Also, coal for steam power came in. And third, there was a new transportation system in the form of rail, and steam-powered engines were put on locomotives, so communication. Communication, energy, and transportation changed, and thereby the economy grew. Then the second industrial revolution in the United States from 1870 to the start of the First World War. The telephone, which Jeremy Rifkin makes a really big deal about. He says the internet people could perceive of, but the telephone was a really big deal. No one could perceive. And all of a sudden, you could call from one side of the United States to the other instead of having to send a letter. So increasing productivity. Oh my, yeah, this is obviously a big deal. Telephone, and then energy-wise, the Texas oil came in. Texas oil wells. So a new form of energy. And then Henry Ford put everyone in the combustion engine, and we could start to move people around, and we can start to transport goods across the whole world. And of course, with that, shipping and all that air freight that we have now. The problem is that the argument from the economics people is that this has only a 20% aggregate efficiency. And of course, there are a lot of chemists here in the room, but there may also be others. Aggregate efficiency is that when you have a certain amount of work that you get out, divide by the amount of work that you put in an inefficient process, that number is low. This is a very inefficient process because of the vertical integration and the loss across all the steps in the value chain that you have. So if you think about these two industrial revolutions, there is a common theme here, and those are the three I've mentioned to you. And those are also the argument behind the third industrial revolution that we are in the middle of now. New form of communication, new form of energy, and new form of mobility leads to a new way of governing our economic life. It leads to how we socialize, how we interact, and thereby grow the economy. So that is then argued to have a theoretical limit of 60% from the financial people. So we are right now on the brink of this for increased productivity and, of course, an increased GDP. What is that then for the third industrial revolution? Well, you probably figured it out already. A new form of communication is what is called the Internet of Things. It's essentially sensors in everything around the world. In our agricultural fields, in our cars, in our seas, in the air that tells us how nature lives its everyday life. But most importantly, in our buildings, because a lot of the energy that we're using goes into the building. So how we manage that is really important. But it's a complex web of connected information, completely digitized. The other one is, of course, renewable energy. Digitized renewable energy, because it's connected to the grid, and we know instantly the amount of energy and electricity available to us. Wind and solar. So the argument is that if you're stuck with nuclear and oil and coal and gas, you should probably think about investing into so you can smear this transition out, because those are stranded assets. And then, of course, from a communication perspective, it's electric vehicles and hydrogen that is coming on the horizon for increased aggregate efficiency and thereby increased productivity. So, then we have the digital twin. What has this got to do with anything? Well, of course, what I'm talking about up here is, of course, from a country perspective, for instance. When you integrate over the economic activities in a country, this is what you see then. But we also see enormous opportunities and benefits by having a digitized communication systems inside a factory for increasing performance and productivity of a single factory. And in Liquid Wind's case, we're going to build 200 factories all around the world to produce electromethanol. The learning that we can get from a connected communication systems from one factory to the other, we believe is enormous. So a digital twin then, if you have factories all around the world, what that is a virtual world that mimics the life of the real world. And you use things like machine learning to make sure that this mimic here is as close as possible to perfection. Because very seldom can you describe all the chemistry and physics to the level of detail using first principles to describe the equations, so you can actually succeed from beginning. Then machine learning is a key way to do this. And those of you who are in the business, you realize then that this can have an effect on all of these different areas of applications for running a business. And then Siemens and Thomas told me, don't forget to tell the audience that there are many different digital twins that we're talking about here, and they have different life cycles, and they're also connected, many of them. So if you want to build a full digital twin of a plant or a multitude of plants, you have to realize that for each and every part of the development of a factory, you have your own digital twin. And the way that you can describe that they are connected, for instance, is like this. This is then a time frame for a digital twin with regards to order of delivery. What are the steps involved there? Well, it goes in this direction here. For product lifetime, well, then it looks like this, etc. And then you see in here, for instance, that these two overlap and these two overlap. So the full digital twin makes use of this overlap and connects it all somehow. Kostas is probably sitting here thinking now, well, what's the problem you're going to solve? And I'm not going to talk about a problem to solve here, but you could imagine, of course, that one of the things that you could solve with the digital twin is the energy minimization, because sensors across a factory will enable you to minimize the use of energy, especially in times of renewable electricity that we're talking about here. Oops. I won't dwell more on this because I only have 1 more minute. Lastly, what's the advantage then and the value for a business? Well, that depends on the degree of digitalization. And by digitalization, compared to digitization, which is simply, this word here means how you make money on the basis of digitization. So digitization is ones and zeros and numbers, and digitalization is then adding value to your company on the basis of that. So as the digital twin develops and evolves, we learn to observe, we answer what, and then we start to understand a few things. Why is this so? Next step, when are we going to be able to do things? So what's next? And then we have prescriptive, which is then action. Now we know so much about how this factory runs, so we can predict in 1 hour we need to take out a small part of the machinery, otherwise it breaks down. And we have learned that from the fact that we have a digital twin that we can foresee the future with, for instance, on the back of machine learning, that tells us how the factory is going to function in 1 hour. So that's our business. And we added bankability to the whole project by saying that we were going to develop a digital twin in the company, which is, I think, astonishing. But it tells you a little bit about where the world is going in digitization. So in summary, before we come into more hardcore science and more real applications, in summary, well, the world is changing, but it's always been changing. But the pace is always faster in the future than it was before. That's just the nature of the change. When new modes of communication, energy, and transportation coincides, then we have new economic development and new economic activities are initiated. And I believe that the digitization is the basis of which these three principles, if you like, rests on, that allows us to make much more productive work. From Sweden's perspective, I think it's arguably so that Sweden as a nation is extremely well placed here, because we have a broad set of economic activities. I lived before in Australia, where you have a very narrow set of economic activities. And there the economic theory says that it's going to be very difficult for Australia, that essentially just digs up whatever mineral it is and ships it off to another country that makes the money. Sweden is much better in that respect, because we dig up the chemicals and we make something out of it, and we build the whole industry on underneath, so to speak. So a broader set of economic activities. We have a thriving pharma industry, we have a thriving minerals industry, we have etc. Economic activities broad. It's also a nation with very tech-positive people, which is important. And maybe, I think, a key thing here is that we have a high penetration of renewables. Because going to stranded assets or locking in a company into a second generation, industrial generation energy source is not going to work. And I do believe that we have an opportunity to lead. Perhaps on the basis of what we'll hear from Kostas here today, and how we can work with your company in the future to enable the development of digital twins. With that, I'm going to end here. I'll invite Kostas to the scene, and then after the 3 talks, we'll have a summary session, and there'll be questions afterwards, and a more open discussion. Kostas?
Thank you. Let me see if I can find my presentation. It's on the desktop here. Very good. Well, good afternoon, everybody. First of all, I'd like to thank the organizers, Magnus and the organizers, for inviting me to this event to give our perspective of the digitalization business. I'll be talking about machine learning in the context of digitalization. And this is the title of my talk. I come from Process Systems Enterprise, which is a provider of advanced process modeling technology. Probably we'd like to think the world's most advanced. We were established in 1997 as a spin-off from Imperial College in London. And towards the end of last year, we were acquired by Siemens. So we're part of the Siemens Process Automation division now. I also have a second hat. I'm a professor, and I've been a professor for many, many years, decades at Imperial College. And actually what I've been doing, I've just been counting, for the last 37 years is designing technology, designing process modeling, technology, coming up with what might be the next generation and so on. And this is just the next step for us. So I'll be talking about digitalization, and really I'd like to address this question here. What is the substance behind the hype? Obviously, like every new trend, digitalization is attracting a lot of hype. There are many claims being made, some of which are exaggerated. And of course, inevitably, there comes a disappointment and so on. But what I would like to convey to you is what is real there. Okay? So obviously our perspective. On the other hand, I have to say we've been doing a lot of work in this area, practical work, devising and installing technology at many different sectors of the process industries, from upstream oil and gas to pharmaceuticals. So we have a bit of a perspective. So this is what I want to talk about, just generally about digitalization. Then I will look at process modeling with digitalization, which is a very, very important component. And then I will talk about something called digital applications in a very specific sense. As I said, we work across the process industries, but mindful of the fact that the next speaker is coming from a pharmaceutical background, I will focus on, I'll take an example, just to make it very concrete, from the chemical industry. So we have a bit of complementarity. So digitalization, well, everybody's talking about digitalization. What I have there is the homepage of BASF probably a year ago. Okay, now this is the world's largest chemical company. I challenge you to find the word chemicals or whatever in here. It's all about digitalization. It's about how these things are going to change the world. It's everything. There's no mention of chemicals and so on. In fact, barely a week passes by. I think now with the coronavirus, there's a bit of a slower pace, but barely a week passes by without some big corporation announcing a new digitalization initiative, a new department for digitalization, and so on. The obvious question is, what is it? Okay, because it's very easy to say, it's going to change everything, it's going to do this and that. What is it? Okay? And one of the main drivers behind digitalization and the whole story behind it is management consultants, because of course, they can see this as an opportunity to introduce new models, new business opportunities for everybody. So this is there are many reports like this. This is a report by McKinsey, which explains how digital and digitalization will have an impact on the process, on the chemical industry, okay? And of course, you can see statements like this. This goes on for quite a few dozen pages. The interesting thing here is if you do a global search and replace, and you replace the word digital by use of computers and IT, you can read the whole report. It makes absolute sense. So of course, none of us would disagree that you have to use computers in the process industries and so on, right? But this is not really the question. The question, perhaps, instead of asking, what is digitalization, what you should be asking is, what is new? Is there anything new there? Is there some new opportunity? Because, yes, we've been using computers. The oil industry has been using computers since 1958, okay? So this cannot be what you're talking about here. So obviously, a company like us whose entire living depends on this sector and so on, has spent a lot of time looking into what is real there. And when you actually dig into it, digitalization really, and what you see now, is advances in 3 main sectors, okay, of technology. And as it happens, they're all IT technologies, okay, as opposed to process technologies. That's a different area of advancement, let's say. First of all, it's about data, okay? We have a lot more data. If we have plant data, we have a lot more sensors, we collect a lot more data. They cover a much wider range of quantities. So for example, we measure a lot of composition in real time, a lot of composition-related quantities and product quantities, which in the past we couldn't do this in real time. They're high quality, the sensors are much better, but the most important thing, perhaps from the point of view of IT, is that this data is accessible. I can build applications on a machine like this, which can access data from a plant across the world, and many different plants, and I can do some complicated applications with that. So accessibility, the cloud and all that is very, very important. The second area is computation. Obviously, you have a lot more computing power. Even in a machine like this, I have 4 cores or whatever. This power comes at a much lower cost, it's obvious, but again, the new factor there is flexibility. I can take my credit card out, I can go to Amazon Web Services, and I can secure 1,000 processors for the next 5 hours. That's what I need, okay? I couldn't do this before without expending a huge amount of capital to get this computational capability. So that is a step change. And the third area, of course, is algorithms. We're talking about machine learning, okay, it's data-driven modeling, surrogate modeling, and so on, but I will come back to that because this is much closer to this presentation. Now, is this all new? Has it come out of nowhere? No. This is evolution rather than revolution. If you actually go back, you will find that all of these, or most of these anyway, have been coming for at least 10 to 20 years. So what has changed now? They got to the point that they can do something useful. That is the difference between something which is in principle possible for someone who's really determined to something which is possible every day to anybody, available to anybody, okay? And this is what has happened in a lot of these things here. We've got to the point now where they can help solve practical problems. So evolution rather than revolution. Now, if you're an academic, you're very exercised about who thought of this first, you know, is it really new or not new? But from the point of view of industry, all you care about is, can it do something that we couldn't do before, something useful? So what we have really there, and this is a very classical picture, this shows the life cycle, it's a very standard picture of a life cycle of the process industries. So if you take any particular process, you start with very basic R&D over here, okay? You learn about your process, the chemistry of the process, you put the concept together, you put a sort of code, then you go into engineering, from R&D to engineering, front-end engineering design, detailed engineering, design the control system, and so on. And then in the end, at the end of the engineering design, you have a design, you build that, and you get the process running, okay? And then you get all the way to, for example, controlling the process. So this is a very, very classical picture. So what is the impact of those advances across this whole spectrum here? Given first an overview, then I will zoom into the right-hand side of this picture. But I think it's pretty obvious that if you have a lot more computing power, a lot more data, you can perform individual tasks better, faster, and cheaper. Yes, that's pretty obvious. Something which is not so obvious is that activities which in the past were being recognized as being independent stages in this life cycle, we now have the capability of merging them. What's the point of merging them? The point is that they are not really independent. In fact, we treated them as independent because we couldn't deal with the complexity of having them together. And in reality, there's a lot of iteration between them. You design your reactor in detail, very good. Then you try and do the whole process design optimization. At this point, you throw the very detailed design you have here, you put a very approximate design, you get this optimized, then you realize that actually the reactor doesn't behave like this, so go back to this, come back, and so on. We can now eliminate this. And now we begin to get published case studies where these things are being merged, we get much better results, much faster. Results as in real processes, process performance. We can integrate workflows like from front-end engineering all the way to control design, all the way to uploading the control code into the DCS. Okay? So there's a lot of integration and data transfer that takes place here. But the most exciting thing is the things we really wanted to do and we couldn't do in the past. All the others are things we could do all the time. And I will come back to that to show you the extent to which digitalization is transforming the operations section to an amazing extent. So all of these things require understanding of the process. And understanding of the process is a process model. That's what it is, really. And here is where we encounter machine learning for the first time. Machine learning is just a way of deriving a model of the process. And what is a model of the process? It's just basically a relation between the things you control, the decisions you can make at the design of the operations, the things you don't control, the external disturbances, the ambient conditions, the prices of oil, and so on, the commercial environment. So these are the sort of inputs. So it's a relation between the things that go in to the things you care about, key performance indicators. You care about the process, the product quality, the process performance, the economic performance of the process, and so on. So the story behind machine learning, on the surface, is a very simple one. Well, I said we have a lot more data. So if I have those data and I apply these machine learning algorithms, I get a model. Machine learning, for those of you who are not very familiar with what it is, it's just fitting. It's fitting of curves to the data, okay? It's a bit more sophisticated than what I'm applying there, okay? There's a lot of developments there, but in reality, in the end, it's just fitting. But you have a lot of data, so you can get a model. So the story is quite simple, okay? You can actually do this very, very quickly. If someone gives you an Excel spreadsheet with lots of data, you can get a machine learning on it and get a model in matter of minutes. So that's not really the question. The question is not whether you can get a model. The question is it going to be a useful model? And that's where it starts going wrong, to be honest, okay? The first aspect there is that I said you're going to build a model, a relation between the inputs you can manipulate and the outputs you care about. Well, I think it's pretty obvious that if you're building this from data, the only inputs you can consider are the inputs which vary in those data. If your data, for example, if I'm designing a reactor and my data does not include different points with different catalyst shapes, there's no way this model will predict the effects of catalyst shape. Just be very plain. And so on. This goes on and on and on. So this model is actually limited because of that. Of course, I'd like to predict all these key performance indicators, but again, the model will be limited to whatever outputs can be measured. So if I can only measure temperatures and pressures, there's no way this model is going to predict molecular weight distribution of my polymer, for example. I think it's pretty obvious statement, isn't it? The third one is that even if you're willing to accept what I've just said and say, good, let's just get on with this, what you have to realize is these inputs here obviously have data which have a certain range of variability of the inputs. You cannot build a model which is outside this range of variability with machine learning because all the information you have is those data, and those data do not go outside the inputs. But the most important thing is this one here, that data is not the same as information. Okay. I may indeed have gigabytes of data. I do, okay? Now, I've been to a nice presentation by a very, very large chemical company where they presented their experience with machine learning. They showed how they collected, very hopefully, they collected data from a plant. I can't remember whether it was 2 years or 3 years, but it was an absolute massive amount of data. And they said, well, surely I can build a model out of this. I mean, if I cannot build a model out of this, what can I do? When they analyzed those data, they found that in those gigabytes of data, there were 7 distinct points. So it's like telling you, can you build a model with 7 points? Well, you can barely draw a straight line, 7 points. I mean, you can just fit, yeah? So that's a bit of a problem. So the useful data is not necessarily big, okay? And the real issue is, if you think about this, is that the job of if you're collecting data from a plant, the first priority of the plant manager is to give you 0 data, okay? If he or she is a good plant manager of a continuous plant, they will aim to keep the plant at the constant operating point. If they're successful, you have 0 data. Well, you have 1 operating point. There's no way you can do anything with that, okay? That was a much bigger company and so on. They managed to find 7 points, but that's just like not enough. So there is a fundamental problem. A lot of that is driven by misunderstanding. The FANG analogy. FANG stands for Facebook, Amazon, Netflix, and Google, okay? And these guys have done amazing things with machine learning. However, their situation is completely different. When I log on to Google Maps, yeah, today, just today, or in the last hour, how many millions of people have logged into that? How much data has been collected from them? Completely heterogeneous data. There's a lot of information in those data, okay? We haven't got anything like this, okay? Not so much, not even in data, but definitely not information. On the other hand, we have one thing that works for us, that they are trying to model human behavior, trying to model the likelihood of you buying a new pair of shoes in the next hour. We're only trying to model some gas and liquid in a tank or some solids. It's a lot easier. So the processes are much better understood. So the point I'm trying to make is that data on its own is not enough. First of all, it's not big, and information is even smaller. So unless you combine it with prior scientific engineering knowledge, okay, you're not going to get very far. And we have this experience, other people have this experience, and so on. I can give you probably 2 or 3 cases where this doesn't hold, and people manage to get a lot of the way down the road in areas like predictive maintenance, just by analyzing vibration data on compressors, for example. The examples like that are very few, and in fact, it's the only one you're going to hear. Okay, pure machine learning doesn't really work. What you have to do is complement the data part with the fundamental knowledge. Because the fundamental knowledge doesn't actually have to be first principles. It could be empirical engineering knowledge. But the key thing is, it was derived from information which is independent from our own plant. Okay? Prior knowledge in statistics. Anybody who has statistical background, Bayesian statistics, but this is a completely obvious statement. It takes a bit longer to understand. So what we're talking about is hybrid models. We can start with a physics-based model. What I have here is a nice, shiny heat exchanger. Anybody with a chemical, mechanical engineering background knows how to write down the equations which describe this in 2 seconds. I hope they do. And when it's like this, I don't need any data, to be honest. I can just predict the behavior just like that. The problem is, it's not like this. After a while in real life, it goes like this. It gets fouled up and so on. So my physics-based model is incomplete. And what I tried to do in that case is to provide a data-driven element within the physics-based model. So what I'm trying to tell you is, just because it's incomplete doesn't mean we're going to throw it away, all right? The mass and energy conservation is valid. Even the concept of a heat transfer coefficient is valid. What perhaps we don't have is a way of calculating exactly the heat transfer coefficient, where then maybe we can bring plant data from this particular heat exchanger to estimate the heat transfer coefficient, or get a correlation with the heat transfer coefficient based on other conditions inside the system here. So this is what we're doing. We are keeping all the valid physics, and we are complementing it with very carefully targeted elements which are derived from data, okay? Our philosophy, at least speaking for ourselves in PSE, is that we go for maximum physics. So we put the maximum amount of physical knowledge we can have. And then, if there is still a gap between what that model predicts and the real system, we patch that using a data-driven element. Other people do the exact opposite. They start with a completely statistical model, but then they introduce concepts of mass balance, energy balance, at least, so that it doesn't lose mass or energy. Yeah, well, to some extent it's philosophical, but at least this is the approach we are following here. Okay, so there are many potential applications area of things like this. Areas like reactors with very complex chemistry, which cannot be predicted from first principles, equipment with poorly understood behavior like catalyst deactivation, heat exchanger fouling, anything which degrades over time is often very difficult to capture from first principles, to be honest. I know we have a lot of experience on this. And then finally, you can have very detailed physics-based models which predict, for example, molecular weight distribution of the polymer now, very, very accurately. Unfortunately, we cannot go from the molecular weight distribution to the melt flow index of the polymer or the density of the polymer. So that final bit has to be patched using data. But data, the machine learning provides a patch. So this is machine learning from data. This is a very quick perspective from our point of view. There's a different kind of machine learning. Okay. Very often, using physics or physics plus machine learning from data, we can build very, very accurate models, predictive models. It's the range of success nowadays is quite impressive. The problem is that although accuracy-wise the model is very, very good, it may be unsuitable for some of the intended applications. As I will talk about later in a second, a lot of the applications we are looking at now are very computationally intensive, and they have to operate in real time. And in those cases, I can have a model which is extremely predictive. Unfortunately, I cannot solve it fast enough or reliably enough in real time. Obviously, if I have an application which is running 24/7, I do not want a failure in the middle of the night in the desert. Okay, it has to be guaranteed to succeed. So what we try and do in those cases is to build surrogate models. Now, this is another facet of machine learning. This is machine learning applied not to plant data, but to data which have been generated by a more detailed model. Okay? The underlying techniques are actually very, very similar. It's the same thing, which I use the underlying model, I generate the data, and I just apply machine learning to produce simpler models. This is a case, one example is something called a gas oil separator plant, which have 5 inputs and 14 outputs. In this particular case, there is absolutely no difficulty in putting a completely first principles, very predictive model of what goes on in here. It's a bit more complicated than this, it's just an idealization. But yeah, no problem. The problem is, we want to nowadays model systems and optimize systems in real time, which involve 100 of those together, plus many other bits and pieces. And that's the problem. We can put together the first principles model, but we cannot solve it fast enough. So what we're going to do here is we're going to apply machine learning to build an explicit model, an explicit relation between the inputs and the outputs. So what we do is we take the detailed model. We have now very systematic techniques of generating data from detailed models, something called low discrepancy sequences, Sobel sampling, in case of any of you have heard of the term. So we generate these data points by sampling completely the input space of the detailed model. And once we do this, we have techniques, machine learning techniques, which can actually take those data and automatically derive expressions like this. So the key thing here, you don't need to understand the details, the key thing here is it's an explicit expression for the output as a function of some of the inputs. And everything else is determined automatically. It's press the button and you get the answer. So these are different kinds of machine learning. Now, this technology in particular is actually key. The reason is that our capabilities in process modeling and digital applications and so on are growing by the day. However, our ambitions are growing even faster. So it is very, very difficult to reconcile our ambition with our capability. And the surrogate modeling allows us to cut the link between how detailed, how accurate the model is, and how complex it is computationally. So we can take models now, we can build the most detailed model we know we have physics for, or data for, not worrying too much about how computational complex it is, because we know that once we build it, we can apply surrogate modeling, machine learning to it, and we can compress it into something which is much more compact. Okay? In the old days, I would say, oh yes, I can describe this phenomenon much better, nowadays, because we understand it a lot better. And you would say, yes, you can, but you'll never be able to solve that model fast enough for the application you have in mind. So that's it. The conversation ended there. Now they say, no, don't worry. Let's build the model. Let's put all the physics, all the understanding we have in here. Because when it comes to it, we will cut this link and use surrogate modeling. So it's a very crucial technology. Okay. Now, the final thing I want to mention is an area where digitalization, all these technologies, so far I've been talking about the tools and the machinery and so on. I want to focus in an area where we are beginning to see the impact, real big impact. And this is in process operations. In my life cycle, it is the bit at the far right. We've designed the plant, we've built it, it's running. Okay, and the question is, how can we make it perform better in real time? How can we make it more robust? How can we make it more predictable? And a very classic way of understanding process operations is this standard hierarchy. Level 0 is the plant. Level 1 is the regular control, the DCS. Level 2 is supervisory control, things like model predictive controller and so on. Level 3 is plant operations management, like things like real-time optimization of the plant. And level 4 is supply chain. Now, what is the new? This has been like this forever. What's new here? What is new here is the fact that we're beginning to be able to take very detailed models of plant behavior and solve them in different ways in real time, 24/7. So essentially what we're doing is we are injecting very deep knowledge about very deep understanding about the behavior of process into plant operations. Until now, those of you who come from this area will know that most of the plant operations applications rely on very simple models. For example, if I do model predictive control, it would be linear MPC, and you use a linear model, which doesn't rely on any physical understanding. You just go to the plant, you kick the plant around for weeks on end, and you see how it responds. You make yourself extremely unpopular with the plant operators and the plant manager because you disrupt their plant for weeks or months, okay? And in the end, it doesn't work that well, but that's it. Nowadays, what they're saying is, forget all that. We have all these physics-based models of polymerization reactors, okay? So we can actually use them. Now, I chose these applications because they're all real. This is ExxonMobil polymerization. This is SABIC monitoring yields in real time in an olefin cracking furnace. It's also SABIC monitoring the degradation of the performance of the cracking furnace over time because of coking. This is the Hemmelot plant in the Netherlands optimizing a whole utilities network every 15 minutes, continuously for years now, several years. That is oil field optimization. I'm afraid I cannot really tell you what it is, but it's actually optimizing an entire oil field. And this is the ultimate in complexity is, until now, we would be so satisfied if we could optimize one plant to real-time optimization. And that thing there is optimizing 13 gas plants as a single entity using very detailed models every hour, and the solution takes 10 minutes. Okay? This is beyond what we could dream of as recently as a couple of years ago. And now we have the technology for actually doing this. So all of this has been achieved because of combination of those developments I mentioned. The fact that we have the data to draw on, we know what's happening in this network of 13 plants. The fact that we have the computational power, and more importantly, the fact that we have the algorithms, the surrogate modeling algorithms and so on. Okay, so there's a huge opportunity. I think, I hope it's pretty self-evident that the more understanding I put into how the plant behaves, the better I can do. Okay. So here we're putting a lot of information into this so-called deep process knowledge. Okay, that's the opportunity. So that's the good news. The bad news is that if you actually look at the details of each one of these applications, on the surface they appear to be completely different. Now imagine, from a very practical point of view, someone trying to develop 100 different applications, each one of which has a completely different code base, a completely different approach, a different way of dealing with integrity of data, and so on. That becomes unsustainable. So one of the things that PSE has been doing in the last few years, in very close collaboration with ExxonMobil, is designing the next generation platform for building these digital applications. Something called GDAP, GPL Digital Applications Platform. I don't really want to go into the details. It's a very complicated piece of software. In terms of complexity, each one of these pieces here is solving one of these very, very big models, but in reality, you have multiple applications talking to each other, calculations talking to each other in real time, talking to external data servers, talking to the DCS, talking to historians, talking to web services like the weather, what's tomorrow's weather, because you have to optimize, talking to SAP to get commercial data and so on. All of this in real time. It doesn't have the luxury of failure, so it has to keep going at all times. So we've built this application. Again, as I said, I don't have time to go into this. And this platform allows us now to have a very uniform approach to how we develop more and more complex digital applications at very low cost. It all sounds very abstract, so I'm going to show an example. So this is a real example. It's lightly disguised. It's an application that's been running in Korea. It passed the site acceptance test in August. And its job is, and what makes it nice is that it's a bit easier for me to explain in a single slide. In every olefin plant, you crack hydrocarbons and you get ethylene. Unfortunately, in addition to the ethylene, you get acetylene. Now, acetylene is a no-no because if it gets passed on with the ethylene product to polymerization, it just causes havoc in the polymerization reactor. So every ethylene plant has a unit whose job is to remove the acetylene. Concept is very simple. You have acetylene, you put hydrogen, you convert it to ethylene. So it's a win-win. You get rid of the acetylene you don't want, and you get ethylene you want. The problem is, there's nothing to stop the ethylene, which you spend so much money to produce, from hydrogenating to get ethane, which is where you started. So you gain some ethylene there, you lose some ethylene here. So of course, you want to maximize the net ethylene gain. What you gain minus what you lose. And just to make things more interesting, of course, because that's how life is, while you're doing all this, there are certain side reactions which deactivate the catalyst. So if you're not careful, you may think you're doing great, you're getting rid of all your acetylene, you're getting some ethylene, you're doing great, right? No, you've just destroyed the catalyst. You have to stop the plant and regenerate the catalyst, okay? So what we are looking for is to maximize the net ethylene gain, what you gain from the first reaction minus what you lose in the second reaction, but to also increase the run length, how long it takes before you have to regenerate the catalyst, by minimizing these reactions here. You can play with a lot of things. These reactors typically are fixed bed catalytic reactors, so you can adjust the amount of hydrogen you inject there, you can adjust the temperatures here, and so on. A few other bells and whistles, doesn't actually matter. And you can try and run this online to run the plant. Now, modeling something like this offline these days is nothing. Okay, we can actually model this to the nth degree, have very accurate predictive models, and so on. We have offline modeling tools which can do this very, very easily. But what we want to do is not an offline tool. We want an online tool which will take this model and 24/7 run the real system. So what I have to show you here is the real system pretty much running, if I manage to start this video. Oh, yeah. This is pretty much the real system. As I said, it's running in Korea. It's a two-bed sequential system, 2 reactors there. These are it's a web-based dashboards, but it's not just pictures, because underneath there is the very, very detailed model running in real time, being solved in different ways to give us this information. So what I have here is measurements coming in real time. Of course, as everyone knows, what you're measuring is not necessarily the truth. Okay, the measurements may be inconsistent and so on. You need to reconcile the measurements. So what you're getting here is not what is being measured directly. It's not what is being measured directly, is what is estimated. So this is what we think you're doing. And then the system says, yeah, this is what we think you're doing, but we think you should be doing this. Okay? So every few seconds, the system says, no, you're not doing the right thing. You should be moving up. You should be moving down. You should be increasing the temperature here by 2 degrees, 2 degrees lower here, add some more hydrogen, and so on. Okay. The other thing that a system like this does is that it gives you in real time a view of what's going inside the system to the extent that no amount of sensors can measure. So what you're getting here is the acetylene profile inside the bed. There's no way you can measure that. But we can actually tell you. It gives you a lot of insight as to what is happening right now. Okay? How is this achieved? The details are not very important. What is important is it can only be achieved by combining data from the plant with a very detailed mathematical model of the plant. Neither the model on its own, nor definitely not the data on their own, can actually achieve this effect. This is a key message from this talk. Okay? All sorts of things here, which one of the things that systems like this are they are very aware of their own limitations. Continuously, they monitor their own performance. If you have failures, they need to be reported to the engineer who's coming in the morning. The failure happened at 2 o'clock in the morning, yeah? But there's nothing you can do, just have to keep going. By the morning, You have to allow the engineer to completely debug that one case that failed. Okay. All of these things is handled not by some ad hoc code, but by this digital applications platform that we have co-developed with ExxonMobil. So I'd like to finish. I hope it gave you a flavor. I appreciate it's very fast and so on. But there are three key things I'd like to convey to you. There's a lot of hype about digitalization. And as always with this excessive hype, there is a danger that people will switch off. What I want to tell you is, yes, there's a lot of hype, but there are substantial new opportunities, okay? We really do have new power and capability, which allows us to do things we couldn't imagine a few years ago, okay? And this goes all the way from R&D to engineering design to operations. However, where we see the immediate effect is in operations. This is what Magnus said, because I keep saying this all the time. The important thing is to retain the focus on what problem are you trying to solve. You know, when I say, what do you want to do? And you say, I want a digital twin. No, well, digital twin is not an objective, it's a means. What problem are you trying to solve? And unfortunately, we find that it's a bit of people getting sidetracked. So we need a digital twin, we need machine learning, we need to do this. No, we're trying to solve the same problems we were trying to solve yesterday. It's just that we can do it a lot better. So that's very important to my mind and is the kind of thing which I always go on about. This cannot be achieved by data alone. Forget what they tell you about machine learning on its own and so on. It will not be achieved. We know it. Lots of people know it already. Already I don't know if anyone knows the Gartner hype cycle. We are very much on the coming down from the peak of expectation. Okay? The reason is very fundamental. The data we have do not contain that much information. Okay? By design, because the data from our plants are designed, or our operation of the plant is designed to keep it at one point. Okay? So the key thing, of course, is that unfortunately, we don't have to rely just on data. We have prior knowledge. We have all this engineering and scientific knowledge we've been accumulating. So the scene is open for some very exciting applications, like what I hope I showed you here. And we are beginning to, until recently, we and people like Honeywell and Amazon and so on, we looked at each one of these applications as like a one-off. Okay, so in fact, there's a completely different division responsible for building this one, RTO, and the model predictive control is another division, and this or another group, and so on. We are beginning to see from the very fundamental point of view that actually you can have sort of a general theory, a general approach for this. And although it sounds to be just a concern for software guys like myself, actually something which will have an impact on industry because this impacts our ability to develop these at a low cost and get them out to industry. Okay? So we've seen all these things, and this is happening right now. PSE on its own, until recently, a small company, we now have 7 full-scale applications running like this. So it shows you the speed with which we can get these things. My final point, bit of a joke. All this stuff is excellent, it's very advanced, it's very exciting. This doesn't mean that you can skip the basics. And it's a bit of a joke. I find this cartoon very, very nice. But it happens to us all the time. Someone comes and talks about very advanced digitalization applications and all that and so on. And then you realize they actually don't have a basic mass and energy balance of their plant yet. Yeah, you really need to, there's no short, digitalization is not a shortcut, it's the next step, okay? Again, that's all I want to say. Thank you very much for your attention. And if you have any questions, try and answer them either later in the session or I'd be very pleased to hear your comments via email. Thank you very much.
So, can you hear me? Yes. So good afternoon. So thanks, Magnus, for inviting me to give some comments, because that is what I intend to do, and share a few examples. So my home base is AstraZeneca, the R&D site in Gothenburg. I still quote it as Mölndal, but that's the geographical location. So my background, I'm actually a PhD in chemistry. I've been adjunct professor in Uppsala for 6 years, and then after that I've been associated to Chalmers for almost 15-20 years. I've been actually at AstraZeneca for 25 years now, and continuously are actually involved in academic interactions and supervising PhDs, etc. And the rationale for that is actually that working in an industry or in a sector where we constantly need actually to push boundaries with respect to what I would call supporting technologies, supporting science, etc. Trying to pave into new ground. So that is what I'm going to talk about. My current role is that I'm responsible and accountable for our science innovation strategies in the area of manufacturing and materials. So the digitalization kind of comes into that corner also, and has for many years, although I personally don't like the word big data, basically, but I will make a few references to life science in general and to AstraZeneca and digitalization. But I will focus a bit on a few of those acronyms, but those are actually a few of real life examples or implementations, not just explorations, but exploitations that we are involved in various parts of our value chain. And at the end, I would kind of build on what both Magnus and Kostas addressed with respect to challenges. And I will emphasize industrialization as one area which needs to be bridged between science and the real life implementations. And that also, of course, refers to how we secure the right expertise, access to expertise, ensuring the skill base where it is needed. And there are some other things I will address there. So the drivers first. So I just borrowed this from the Swedish organization for the pharmaceutical industry, life science industry in Sweden. So you can see that, I mean, the role of life science industry in Sweden is quite significant, and it's starting to be on par with the automotive industry, actually, according to the latest figures from LIF, Läkemedelsindustriföreningen. So AstraZeneca is a big company, 70,000 members and employees. I bring it up in particular because I would like to just emphasize the complexity working in a big corporation, actually, where we have activities, research and manufacturing in almost all geographical regions. So, for example, operations and manufacturing operation sites in actually at 26 sites and different countries. So a big complexity because of that, but also complexity from a materials and science and product range point of view. So we tap in not just to traditional small molecule, fine chemical industry processing, but also into biologics, etc., and what I would call formulated products. But I think also to build on Kostas' comment that maybe the old disciplines are vanishing because, I mean, we see a continuum now. So we also need to rethink about how we structure, how we tackle the exploration and exploitation, both from a science point of view as well as from an industrialization point of view. So also would like to mention, I mean, sustainability is of course in focus in our society and in the globe all over the place. AstraZeneca also have a kind of bold ambition, and which have been raised quite recently. And at the World Economic Forum, our CEO emphasized that we have set targets now to eliminate emissions by 2025 and be carbon negative across the entire value chain by 2030. So much further beyond the current Paris agreement. So that also will have a huge implication also on how we manufacture, how we process, how we design our manufacturing, how we design our process, etc. Typically, on a corporate level, you find digitalization strategies or communications on this level, and what you often see in a pharma life science arena is that there is, of course, focus on patient data, clinical data, etc., etc. Quite much focus, for fair reasons, on the patient and patient data, patient-related outcome data. But often in any life science company, you tend to miss the information that relates to kind of digitalization strategies and the initiatives that underpins the access to healthcare, to products, medicines, whenever they are needed. So the value chain, it's a long value chain in life science, starting from understanding the shape of the molecules that can intervene in the biology of interest. So for fair reasons, there is much focus on the early drug discovery part and loads of data because of lab automation, high throughput screening is generated more and more. And so I just would like to acknowledge Ola Enquist is one of the AZ people who actually is implementing machine learning for better extracting, faster extracting, smarter extracting information from those big data sets. I would say they are more complex data sets, and so trying to capitalize on the advancements in machine learning in general most often have been exploited or evaluated in image analysis, as we all know. But much of those algorithms can actually be applied more or less directly in this kind of extraction. So it's an analytical means that emphasizes and actually improves the predictability. But I will not talk about that because I will try to jump into what is connecting with the process industry and processing. And so digitalization is not new. We've been doing advanced computational modeling and beyond just traditional chemometric multivariate analytical methodologies, PCA, PLS, etc. over the years. So not just empirical modeling, what I call it, for and design of experiments have been a workhorse in pharma development for almost 20 years, I would say. But more advanced, more a priori and first principles modeling is typically have appeared more and more during the last decade using fluid dynamics computation, often quite computationally extensive, etc. But also a learning from that is that you need to get down to the details, because the devil is always in the detail. But then you can push the boundaries, and then you can do model simplification and actually develop simplification because you have an understanding of the underpinning systems, the physics, the chemistry, etc., the interactions in multi-phase systems often. And that is what you see, and those can then constitute kernels for more hybrid modeling, and you can inject them into traditional empirical multivariate modeling also, and thereby get some deterministic kind of direction for your multivariate empirical modeling, which actually helps to straighten out the predictability and improve it. So we have a skill base in that space, but we have started to explore more machine learning approaches. But again, it needs to be driven by something. And that's why I want to emphasize that the driver is not machine learning. The driver is, for example, process intensification. Because the value there from that is a bit more improving transferability of new established processes, improve scalability of new processes, also improve energy aspects, yield aspects, etc., etc. So there are significant opportunities with process intensification. There's been quite much focus on reaction, the reaction area, and examples from Stankiewicz and others there on benefits with process intensification. The analogy here in the more secondary manufacturing or powder processing area is and formulated products is actually the powder processing, where we transfer into continuous sets and continuous powder processing and integrating them in integrated systems. So traditional tablet manufacturing has been batch-wise for a very long period, but you can integrate them in a very small geographical footprint and then use it for much more improved flexibility in your manufacturing operations. And here is actually some results from collaboration with university in Eastern Finland. So why? Well, because in Europe at that time point, it was around 2012, there was only 2 test beds for integrated continuous tablet manufacturing. One in Ghent in Belgium, and the other one was established in Kuopio in Eastern Finland. In Sweden we still don't have any, but we actually have a GMP facility that is continuous tablet manufacturing in Gothenburg now. So thanks to tapping into academic centers and expertise and working collaboratively, that is a possibility. So you can find some good examples that have proven and demonstrated the benefits, but also some challenges with transforming batch-wise traditional powder tablet manufacturing into continuous and what it takes. So now I will connect into the digital twin world. So having set up the continuous tablet manufacturing, it's quite logical that we in parallel have been working with ensuring that we have a virtual representation of that. And that's not just integrating the different unit operation models, but also integrating it into a total system. And there, in this space, we have also worked collaboratively with PSE and integrating models that they have had, but we have also experience from developing sub-models, and the GPROM's framework there enables you as an end user actually to have some flexibility on integrating some underpinning sub-models that are kind of company specific or material specific. So starting to get some real nice results, and we're starting now to approach a more implementation stage on that in business as usual activities. A couple of words around that it's not trivial to do it. You need to have reliable underpinning models that can be connected. The second aspect is, of course, that you need to have a kind of business objective why you do it. I mean, what we see as a possibility with the digital twin is, of course, that not just operating the physical unit, but actually taking shortcuts when we establish new processes for new products. We can do that virtually, do the designer experiments in the twin, and then define the set points, and then more or less push the button and get going directly. So we cut times for getting into operation, and that it will improve the flexibility also from a development and transferability point of view. So the combination of process intensification, which is built around and founded on a high digitalization approach for your unit operations and your system, combined with ensuring that you integrate from beginning, establishing a virtual representation of your advanced new processing system, helps to explore challenging situations. The other example, which we haven't addressed that much so far, much is focused around underpinning models and how to combine them into systems and thereby create digital twins. The other area is, of course, the analytical opportunities, advanced analytical data analysis means. But the third area is optimization opportunities, self-optimizing algorithms. And it's not just automotives that can be equipped with self-optimizing, regulating algorithms, but also a reactor can do that. So here we have been collaborating with Professor Bohan in Leeds University, and Graham Clemens is one of my colleagues. He's based in Macclesfield. And what has been done here is building actually a lab-wise flow chemistry system, which is very flexible with respect to valves, pumps, etc. But it's also equipped with online sensors, PAT sensors. So thereby you get a feedback loop from what you monitor as outcome. And you can use that for optimizing your new chemistry, your new synthesis, your new reactions in a lab scale format, and then transfer it into a larger scale processing. I think the obvious benefit from that is that in an industry which have been dominated by design of experience for so long time, we can take shortcuts, sound shortcuts now, because after first experimentation, the next experimentation will be based on the outcome. So you get faster to the optimum thereby. So compared with doing a similar or a parallel design or experiment, you will actually do it in a much shorter time through fewer experimental points. And just to show that the algorithms that was used here in this implementation is called SnobFit. There are numerous algorithms, so we will not go into the details. The key point is that that is one of the more established that works quite well with new reactions. It's particularly useful for quite one single step reactions, so it works quite well. But it has been recently also developed further, so it also works with multi-step reactions. But you can see here from the surface here that comparing traditional, traditional simplex optimization here in a maximum of 30 steps, it kind of moves around there, whereas the orange dots here is actually the SnobFit algorithm picking experimental set points and thereby cover a much larger space from beginning, and thereby also much faster finds the optimum that is within these centers here, the 3 centers. That's just a simple example of how you can actually gain benefits from machine learning algorithms in a very simple lab setup. But I will end this with showing another example here on machine learning. That is the interface of what I will call discovery of new molecules, designing lead molecules for new drugs or optimizing them, and to the scaling of and establishing the manufacturing process for molecules. One of the challenges with many of the new drug molecules is, of course, that they are quite complex in structure. So it's a huge challenge how you build these new complex molecules. And one of the challenges there is to find the right asymmetric catalysis means for achieving that. Per-Ola Norrby at the Gothenburg site has done some very nice work very recently here. It's based on using actually a quantum mechanics kernel at the basis, and for developing a lookup table, and then that that is fed into a machine learning algorithm that also combines that with a historian on different structures, as you see here, a library of structures. So it becomes a virtuous screening, so you get a faster help as an aid for designing your catalysis means for building the new molecules. So it's a very nice example of bridging between fundamental first principle a priori type of modeling and machine learning and optimization. So those were the few of the highlights, and as I mentioned, there are some key collaborators from AstraZeneca here that you could approach if you're interested in any of these. I also forgot to say that talking about the digital twin for the tablet manufacturing, that's a collaboration between a site we have outside Manchester in Macclesfield. Gavin Reynolds is the expert there, and he's working together with two of my colleagues in Gothenburg, Louis de Chuan and Johan Remmelgas. So we are kind of collaborating across the pond. So you can say that looking a bit retrospectively, the last 10, 15 years, there is a journey, I mean, from just empirical regression modeling through to more mechanistic, but now combining the relevant tools into hybrid approaches. The other one is that going from just having models for a single unit operation through to actually model complete systems and to combine them into system structures. And the other one is that going from having models just for a single phase to multi-phase systems, as well as single scale and to multi-scale. So the complexity increases tremendously by all these aspects. And everything at the end kind of established the foundation for the new opportunities from an industrial point of view. And it's to move away from just understanding things in a post-analytical way to not only predict, but actually do predictions in real time. Means actually that the boundary between traditional control engineering and what we are referring to here is also vanishing, which is an interesting observation in general. So what is control then? Maybe we need to redefine the word control. So, a few challenges to sum up. I borrowed this figure from a publication in International Journal of Pharmaceutics from 2016. It's actually from FDA. is an expert group in FDA. They commented as a response to the Obama's initiative on precision medicine that they frequently see a challenge with respect to industry, academia, and new technology. That this gap between the academic scientists and the private sector, the industrialization. So bridging, and so there is a huge effort to bridge. So it's not just a gap. That is what we have encountered over all the years. So it takes not just access to a skill base and experts, but it also you need to take height for the effort that is actually required to bring this into exploitation and implementation. And of course, in pharma, lab scale processing has historically been a bit Stone Age when it comes to digitalization, PLCs, etc. In full scale manufacturing, it's integrated, but not in the development equipment and systems. But again, I also would like to emphasize that there are a number of different players here, and there are few standards. We have some standards for big scale commercial manufacturing, control systems, process automation systems, and some equipment. But that's an area where it would be interesting to hear Professor Kostas to comment on that later on. But actually, I would like to end then with commenting on that everything at the end is driven by value. So if you think for a few minutes, I guess that most of you have probably tested flight simulators sometime during your younger period of life. And you can think about the flight simulator, that's a toy, but there are flight simulators, professional ones that are used for training pilots. And there is a value of doing it in a simulator, which is actually a kind of virtual and physical representation of the big machines. The question is, what will it take for us to take our physical machinery and have a representation that is virtual? So again, think about cars. Most of us still do training in the physical car. Why don't we do it in a digital twin? So there is a return of investment aspect that still need to be thought about when investing in digitalization. Is it the right timing, and when is it? The other one is also related to cars. If you think about self-driving cars, I mean, there are self-driving trains. The metro in Copenhagen has been self-driving car-based machinery for quite many years now. So what is actually needed to take self-optimizing or self-driving cars all the way through? Well, of course, it's about safety, risk aspects, risk to society, to individuals. That's something that need to be brought in. I mean, what level of predictability is acceptable if you have a very sensitive system? So all those aspects will at the end, not at least in a regulated industry that I'm within, come into focus sooner or later. Yeah, so in summary, from a life science and an AstraZeneca point of view, I mean, the drivers is patient centricity, the value to patients, as well as sustainability, as you saw. But process intensification, not just digitalization, are actually the opportunities for us here. But I would still emphasize that the industrialization is not trivial in all areas, and that need to be considered thoughtfully. But it also requires access to expertise, and I think there is some needs also from a Swedish local point of view in this space in order to take this into an industrial success. So with that, I close.
So I think now we open up for questions and comment. Maybe just a quick comment for me. Kostas, I remember you have in GPROMS also a material science platform, don't you? Not just process, but we heard you saying that the process and optimization being one business case where you saw clear advantages. But now we see also from a material science perspective, machine learning is coming into the picture.
This is very important. I think especially the example you showed with the quantum mechanics being integrated. Because at the moment, our use...
Stand up, please.
Sorry, our use of those techniques in process is actually quite limited so far. Yeah, and a lot of this is computational. And what you showed actually is a very good example of what I call the surrogate model, where we do certain calculations, and from there you create a lookup table, and from there you create a model from there, and then you can use the model within much higher level calculations.
Yeah, he has a deep voice, so maybe you can hear him all the back. But is it on or not?
Yeah,
it is on. Sorry, thank you. All right, so I think now we just open up for questions and comments from the audience. Please. Martin.
A question to Staffan about, so yours is a very highly regulated field of industry. I was wondering, do you feel that the regulating authorities are, you gave an example where FDA was demonstrating the whole thing with the translatability and industrialization of small early products, especially in the public. But in terms of what these recent developments in tools, what does that mean for quality by design considerations? And is the regulators pushing? Are they in the forefront? Are they responding? Is there a difference between Europe, EMA, for instance, and the FDA? And what's happening in that field?
So I mean, the simple answer is that any agency and also the industry never will compromise when it comes to safety to patients. So that's one. The other one is, of course, that the challenge regarding access to expertise and skill base is the same for health agencies. So it's a society responsibility on how we train and educate. So that's the simple answer.
I think if I can just add to that, of course, we are all learning. The FDA is learning, beginning to learn how to use some of these tools. One of the key aspects is we're moving away from tools which give an answer as a number to tools which give probabilities. Okay, and a lot of the technology we have introduced recently has to do with assessing the probability distributions of outcomes. And that, that is very, very closely associated with the risk. Yeah? Because in the past, we would just do one calculation, maybe try a few case studies and so on. But now we can systematically explore the entire domain. And of course, in pharma, we have uncertainty in the models themselves. Okay? And then if we go to performance, drug performance, then we have intra-patient and inter-patient variability. And that needs to be assessed. So, for example, we do have models which predict oral absorption and things like this. But, of course, there's a huge amount of uncertainty and variability from one person to the next, so even within the same person. So this is driving technology in certain ways, modeling technology.
So when we talk about manufacturing in a pharmaceutical area and regulation, current regulatory frameworks, when you get approval, market authorization for a new drug product and drug substance, the probably most important component there is what is referenced as the control strategy. The control strategy is actually founded on quality risk management. So I think that's where the opportunity is to use the digital twins to better justify the real control strategy. Do you want to comment?
No, I think you made a point actually. In fact, the other point you made is about the boundary between control and this kind of thing is blurring. Indeed it is. Mm. Yeah, I think if you remember the hierarchy I showed, traditionally what we call control now, that's nitty-gritty control, is the lowest level. But now we have the capability of adding more higher and higher levels above that. We have, for example, now in pharmaceuticals, as we go into continuous manufacturing, we have capability for continuous monitoring of what comes out, because there's no longer the luxury of having a batch, taking a sample and analyzing it at leisure.
One over here. Andy.
When you look on this, you talk about the big data and the lack of information, and then you take back that you have the first principle. But if you look on most of these reactions, still, even if they are based on models of quite a number of simplifications and so on. So the backward is, do you use these models also to identify what sort of information you need in order to actually make the whole system more accurate, or what lacking in our basic knowledge?
Yes. So actually, when you look at, for example, you take our ability to describe reactors, yeah? We can now describe most aspects of a reactor entirely from first principles, down to the details of multi-component diffusion and so on. So there are certain elements which cannot be derived from first principles. So for starters, the heterogeneous reaction kinetics, okay, or the heat transfer coefficient between a packed bed and a metal wall. So those things cannot be described from first principles. So at that point, you have the option of either trying to devise experiments from which you will deduce or characterize, identify those phenomena, or adopting a multi-scale approach. So for example, one thing we're experimenting now is with quantum mechanical ways of deriving heterogeneous reaction kinetics. Okay. But our philosophy is a top-down approach. We start, this is the objective. What does our model need to be able to characterize to be able to achieve this objective? Then which parts of that are already known from first principles, and which parts you need to bring in some experimental knowledge. It is very rarely the case, to be honest with you, that you can actually get reliable kinetics, for example, from plant data. Actually, what we do is we design very specially designed experiments, which are, they completely isolate the phenomena one by one. For example, we try to remove the heat transfer aspects from the reaction. So even if it's a highly exothermic reaction, we dilute the catalyst so that you can obtain isothermal experiments and so on. So designing experiments, lab-scale experiments, is in itself a big task. But again, it's a task where you design the experiments to build a model, and then you also use the model to design the experiments. So it's a sort of cycle.
Yeah, I have a question about the backgrounds of the people that are working in these fields, because the professor mentioned that you require some advanced prior knowledge about physics itself, and that you cannot buy, for example, statistics or machine learning alone. That doesn't suffice to work in the in this field in the pharmaceutical industry. Are many of the people, do they have a background in mathematics or statistics, or are they mostly physicists and chemists?
It's multidisciplinary teams, and if you just take a company like PSE, which is a very small company, it's 180 people, so it's not a huge company, yeah. But even with that, we have probably more than 60 PhDs in there. But then if you look at the skills, we have people who are now software experts. The kind of software we're talking about is not the kind of software that in my days any engineer could actually just have a go. Okay? But on the other hand, we have people who are domain experts in reaction, in crystallization, so on. Okay? So I don't think you're going to find one person who has all the background. I mean, I think that's a key message. And you know, also we employ a lot of people with PhDs in mathematics and computer science. Yeah?
My estimate is that you get probably much the same answer in different sectors. So if you take the economy sector, for instance, there the development towards digitization and digitalization is probably much faster than it is here. They hire now experts within AI, you know, neural networks, all these fancy detailed skill sets. But they need, of course, also financial people that knows a little bit about that, so they can talk to each other. So it's about having a mix of skill sets from very deep to broad and intermediate, so you can facilitate discussions. That's at least how the discussion is now portrayed, sort of from the financial sectors, and I believe also in the chemical sector, and will be even expanded more so in the future.
So I would like to comment on that, because the solution is not to train people to be generalists. The solution is to ensure that people becomes flexible, that we combine different kind of competence profiles or skill profiles with respect to if you can drill down or if you can connect in between different parts of the science. So I would phrase it, we need both bridge connectors, bridging people, as well as those that have deep knowledge in certain corner areas.
In the first presentation, you spoke about productivity in society. But what I hear is rather you guys talking about effectiveness, doing the right things, not doing the thing that you're doing in a better way. It's a matter of coming faster to the right conclusions. And in terms of that, you come into behavior science as well, because the ability to manage complexity is different between different people. And leadership in the coming research in this field will be totally dependent on what leaders you choose.
Interesting comment. Yeah.
Yes.
Efficiency and effectiveness are two different things, aren't they? Productivity, as I see it, is much more related to efficiency. Yeah, because it's how much energy you put in compared to how much you get out. And if you're effective, then that simply means that you can reach to the target no matter how much energy you use, just how fast you make it. When I talked about productivity, I was thinking efficiency, and I don't see a discrepancy to what these guys are doing. I'm seeing it the same way.
Yeah, a lot of the applications I was describing are about improved efficiency of raw material utilization, of energy, and so on. Yeah, because that's where the economics come in. Now, effectiveness, achieving the same task much faster, is also very important. In some areas, is more important than others. For example, in the pharma industry, where they're very strong drivers of getting new products to market, if you can replace a traditional DOE, which took 60 experiments, with something which combines experiments and models, and you manage to get away with 10 experiments, you save a lot, well, not to mention you save a lot of API, active ingredient that you don't have, but you save a lot of time as well. Yeah.
But there was a comment also about the leadership. I'm not sure if we addressed that. Can you phrase again what you meant there, please?
It's obvious that what you're describing here takes a lot of capability to handle complexity. And people are different in the terms of being able to manage huge complexity. And you know, for example, way back when NASA developed the work breakdown structure model to put the man on the moon, which is routinely used by big companies today when they develop infrastructure and so on. that is a model for how to handle complexity in the same way as you're describing your computerized models. But it also takes humans to be able to get the best out of these findings.
Actually, in my experience, the biggest trick is how to hide complexity, how to shield the user from complexity. So one of the key things, I didn't read it out, but one of the messages I had, the very last point I had, was that how important visualization is in this. I mean, we have these enormously complex systems doing huge calculations. The operator wants to see a very simple picture which conveys the minimum amount of information he needs or she needs. So it's all about hiding complexity, actually, in these things and making things. Complexity arises if you have systems which require extensive human intervention. So as we become better and better in having systems which can run on their own without too many failures, without too much nursing required, that is, I think, a step in that direction. If we don't manage, you know, I can explain what I'm doing here, and I can get 3 people in the world who can actually do this, but if I cannot hide the complexity, it will be those 3 and nobody else. Yeah. Which, from the business point of view, doesn't make much sense.
Were you also referring to the complexity of the change needed in order to implement something like this, or was it the actual technology itself? Okay, because the change process is, of course, something different, and I have tremendous respect for that, because that's the 2 times I've tried this. Those were the biggest hurdles to overcome, I should say. So, thanks for the comment.
Do you have time for another question?
Of course.
I hope. So, Professor Kostas, you mentioned a little bit regarding focusing on the value that you could provide from the different models when you want to implement a machine learning model into production, something like that. I was wondering about, in your field, what is your experience of how much work do you actually need to put in to have an accurate model and to decide that this is accurate enough and we can actually use this today without spending too much time and cost into developing something and then putting something into production? Yes. So when do you reach the conclusion of this is good enough and let's go with this?
That's a very, very, very interesting question. So you have to go back to the picture I showed. What is a model? It doesn't matter what it is on the inside, but on the outside is a relation between the decisions I control, okay, at the design operation, the external environmental inputs, like prices or ambient temperature at the lowest level. Those are the inputs, and the KPIs. So, for example, the economics of the process. Okay, that's very general. So let me give you an example. In purified terephthalic acid plants, the key objective of everybody is to reduce the consumption of raw material, which is paraxylene, by 0.5%. Okay? You can do a theoretical calculation which shows how much paraxylene theoretically you should be consuming, but you're consuming 1 or 2% more. So you state the business objective as I want to reduce the raw material consumption by 0.5%. What does this tell you about the model that you're going to use? It tells you that the model must be able to predict the consumption of raw material well within 0.5%. 0.1%, yeah? So that tells you how much effort needs to go, how much detail needs to go into that model. And this also ties with the comment I made about uncertainty, that nowadays we can actually, and I can explain to you later if you want, how it is done, we can actually quantify the accuracy with which the model predicts the key performance indicators based on the way we characterize the reaction kinetics and things like this. So that actually gives us a very quantitative, or much more quantitative framework to work towards. Compare and contrast with the work sometimes in the pharmaceutical industry, in the specialties industry, where the processes are so, forgive me for saying this, some processes are very badly operated that even a simple model will give a 10% benefit. Okay? So you cannot answer the question about what is the required model accuracy without first stating what is the business objective, and not in general terms like, I would like it to be more economic. No, I mean, yeah, what are we going to try and do, okay? And if you do this, and by the way, PSE has a checklist, it's a one-page checklist, that these are the questions you have to ask at the beginning of every project, and I can guarantee you that if you don't give correct answers to these questions, you're going to fail. We've done it many times. Not too many, hopefully, but yeah, yes.
Costa's subtle way of saying you should hire him.
No, we're working very closely. But I think we all appreciate that there's a big difference between oil and gas, where everything is really sort of optimized to the nth degree, and the much more complex processes you have in pharma, specialties, agrochemicals.
This is one of the things I was thinking about. I mean, the data input, that must be so different. If you go to an oil and gas, okay, you can measure concentrations of molecules and maybe some molecules, but here you have biological systems even, you have heterogeneity that crosses both the API sometimes, maybe not the API, but certainly the ingredients supporting the medicine and so on that are so complex. Must be a whole different set of...
a bit of, we're moving in that direction. I mean, now we can, for example, the small molecule pharmaceuticals, we can predict their properties, just like we had equations of state for gases and liquids. Now we can predict this. We're making a lot of progress, but there's always progress. But what is your ambition? Then that defines how clever you have to be. The other thing you have to bear in mind is, again, if you want one statistic you can remember, on a 6-month project, model-based engineering project, 4 months will actually go on experiments and analysis of experiments. It is now very easy, or relatively easy, to put together the model, okay, because a lot of the physics is already captured in model libraries, drag and drop and so on. To specify that model, to do all once you have the model, to actually do the analysis, very easy. Getting the kinetic constants that go in that model is the 4 months in the middle.
The experiment gets
the biggest cost and the biggest uncertainty.
We are slowly running out of time, but we do have time for 1 or 2 more questions, should the audience want to, or comments, perhaps.
I have one more for the discovery part. I thought that's really cool, and only last month there was this first drug that was sort of claimed to be fully developed by various AI technologies, went into the first phase clinical trials. But my question is really twofold with regards to the future of the models in the discovery phase. For one thing, how a company like AstraZeneca looks at that hybrid, if you like, the balance between the data that goes into the libraries and the data attached to the different compounds and basically all the way to the more heavily sort of modeling focused activities. So how dry is discovery going to be in the next couple of years? But the other one is related to the business. I mean, an interesting development in the last few years with some pharma companies and some of their compounds is the sharing of libraries and in different kinds of partnership models. Now, in this perspective, assuming that being able to apply this sort of lower cost, potentially, analytical or modeling tools, that could in principle lead to 2 different directions or redirections from big pharma. One is to say that the libraries we have, we're going to be able to process more of those, and we might not be as generous as we used to be on sharing those libraries. The other one could be going the full opposite direction, saying to the small companies that they have partnerships or collaborations with, we're going to open up not only our libraries but also the tools to play with them. So is there any way we can say anything about those directions?
Well, any one of you have a crystal ball? No, I mean, you can look on the evolution. I mean, the big pharma business model have changed, as you know, over the 2 last decades, moving from doing everything internally by yourself to work much more collaboratively. It's also about de-risking and sharing risks. So you see also trade in between pharma companies because you need to focus much more deeper into it's about the knowledge in the biology that underpins being able to establish and develop new treatments and therapies. So I think collaboration, partnering, and transparency is actually a cornerstone of innovation generally. And probably if society don't want to close down this area, I mean that's probably where society can nurture or put the incentives for moving in that direction. We've seen collaboration between pharma when it comes to establishing more streamlined, more straightforward, more risk-based, science-based approaches to clinical trials. So across companies. So I think that's not an unlikely kind of extrapolation going forward. But yeah.
Wait for the mic, Hans-Jürgen.
Having been in the pharma industry for decades, former colleague of Staffan's, one question, I was in chemical development, whereas he was in pharmacy. But anyhow, one thing that we constantly grappled with was the very, very high attrition in the pharma industry. The last figure I remember, a couple of years back, 96% of all started projects at some stage disappeared. So the survival rate is extremely low. Listening to you and thinking about this, how could you approach this? There are a lot of thinking about how you can streamline it, you front load, and you will have heard these kind of business propositions, etc. Incremental change, but not really the breakthrough. I've just come up with an idea. You start from the other end. And maybe machine learning, that's the reason I bring it up here. If you see the opportunity for machine learning, artificial intelligence, to first show that potential molecule, you don't even need to make it. You test it in a system using these technologies that you have so amply described here to show this will be efficacious and even safe in man. And then you work your way backwards. You make the molecule, you do the safety assessment, you develop the process, you make the formulation, etc. At least thinking out of the blue, this could probably halve the development time in average. Maybe. I'm just asking, is this totally out of the box? This is will never go anywhere, or with these strong tools, will it be possible?
Well, any new tool that can help you to strengthen your knowledge base, your insights, of course, can help you to take one step further into exploring new opportunities, new avenues. But
here we're talking about tools which predict the performance of the drug, yeah, in vivo. Mm. That's what we're asking for, yeah. And okay, it's not really my area, but I know, like in pharmacokinetics and oral absorption, you can try and predict the fraction absorbed of different forms. So you can show that certain forms are going to be so insoluble as to be impractical, at least in a certain way of delivering it. So that much I know, but I mean, whether you can predict the pharmacodynamic effect, I think that's not.
That's exactly my question. So maybe I can build on that. Yes. And I'm also a former colleague, but I was more on the side of pharmacokinetics and pharmacodynamics. And I mean, we have utilized the non-modeling and modeling and simulation clinical trials simulations for many, many years. But what I'm thinking about when I hear you, and I think it was very, very, thank you so much, 3 great presentations. I'm thinking when you build in biology and thinking serendipity and thinking about variability and genetic variability and things that we can't predict in a normal, easy way. And then I'm thinking big data, machine learning, artificial intelligence. I mean, we will learn more and more, but how can this help us find serendipity for the future? And those rare diseases and rare things that you cannot easily predict. I'm sure the computers are so much smarter than we are, but can you just a little bit elaborate on how can we make sure that artificial intelligence will not lose biological serendipity findings that many drugs has been developed from?
I'm looking at Jan here because we are pressed now for time for dinner. Shall we allow Staffan to elaborate?
Opened up a new area.
Okay. One elaboration was okay? Yes.
Very short.
Or both of you?
I know nothing. I'm just
not lose serendipity. Where's the human side of things when we let machines take over?
Yeah.
Where's the human factor? Serendipity. Staffan.
I will never let machines take over to 100%.
Well, then you're not following the general AI development, because when that's done, they will take over.
But I think isn't that a nice...
But that was my point about putting up value and risk. We need to be mindful about, safety to ourselves and to society.
But I mean, I'm sure that artificial intelligence and modeling simulation and so forth can help us to save a lot of time and money, I'm sure, in drug development as well. I just think, a good closure could be that we really need this new technology, and we still need people and brains.
But a simple metaphor would be that most of us trust being on an airplane, and there is an autopilot. Self-driving, so to say, but there are pilots at least doing manually or supervising takeoff and landing. So that's one example of reality.
I don't want to worry you, Staffan, but you do realize that the plane you can describe very easily with 6 equations. Your direct compaction line needs 10,000.
A little bit worse.
Yeah, but that's actually the point. Yes. So being in the air is a bit simpler actually from a complexity level.
We are pressed for time now, but we'll allow one final question and then we will go for dinner.
I don't have a question, I just have a comment.
Thank you.
I feel obliged to ask if there's anyone in all these industries that take summer interns that are mathematics students. Feel free to walk up to me and get in touch. Yeah.
Yes. This is the man to talk to
as well.
And there's another one. Thanks very much for the comment. And thanks everyone for attending today. And thank you for Kostas and Staffan for it.
Thank you. Thank you, Magnus. Thank you. Thank you very much.